Thermal physics is what drives the world around us, from the sun's reactions that heat our planet to our body's warmth that allows our muscles to work. We're going to be looking into how we can measure temperature, and we're going to look at thermal energy, where that thermal energy goes inside objects and how it moves around. As this photo of a car shows, the distribution of thermal energy can be quite complex. Engineers want to be able to not only measure that, but model or predict it as well through fascinating techniques such as finite element modelling. This makes thermal physics important to many areas of engineering, including mechanical, civil and materials. So let's get started. Now this is the first lesson on thermal physics, and we're going to start off with thermal expansion. Now you should have covered some of this before, back when learning about particle theory with solids vibrating, liquids sliding and gases moving around. So I'm going to skip over that part now and jump into the applications and problems with thermal expansion. Here are a few examples. We've got a gas flow valve, a bimetallic strip, a wiggly railway track, a fire alarm, well, heat detector really, a hot air balloon and a temperature control valve. So starting at the beginning. Now this is a fantastic place to start. It's a bit complex, but it will let me explain a lot of the principles in one go. Firstly, what does this thing do? Well, it's a valve for gas, an automatic on-off switch. If this was electricity, it would be a dimmer switch for lights. Okay, so that's what we're doing. We're trying to control the gas. The gas goes in here, flows through the little gap here and out here to a Bunsen burner or something like that. There's a hole here so that there's always some gas allowed through, but we're going to ignore that part of it. In fact, I'm just going to block it up. Let's hope it doesn't explode. Now the bit over here is the clever bit. There's a brass tube. Notice that the rest of the valve was not brass. Brass expands a lot when it gets hot, and that's the reason why we picked it. Inside is an invar rod. Now, invar gets its name from invariable, so it's not variable. It does not vary its length much when it heats up. If this rod starts 5 centimeters long, it will stay 5 centimeters long. So let's put that property to use. As gas flows through, out the exit to a burner, the gas burns and it heats up the room. This makes the brass get hot, so it expands. It's going to expand in all directions, but we only care about it getting longer. Now the invar does not get longer. So what happens is the valve gets pulled to the right and the gap gets smaller. Smaller gap means less gas coming through. So the temperature drops. Okay, so that's pretty clever. This valve will make sure that the temperature of the furnace never gets too high. Okay, I think that's a lovely example. We'll get to see a similar one again later on as well. Alright, let's continue with the brass theme with this fire alarm. I keep calling it that. It's a heat alarm really, and let's see why. We've got that high expansivity brass again, this time fixed to a piece of steel. It's part of a circuit, so electricity can flow from the battery, through the contact screw, through the brass and steel, through the bell and back. the bell will go ding. Except it won't yet because we've left a massive gap so electricity won't flow. To get it to go ding, we need to close that gap. So how are we going to close that gap? Have a think. You're not allowed to touch it, by the way. Alright, so if you think you know, pause the video, give yourself enough time to write down a proper answer. Okay, and then carry on. So hopefully you've got yourself a decent answer. What's going to happen is this brass and steel is called a bimetallic strip. And I'll show you what it does. So we've got a piece of brass and a piece of steel. Let's heat them up. They both expand, but the brass expands more. So now the brass is longer than the iron. What the engineers realised is that if you fix them together nice and securely, they will bend together, like so. To see why, let's look at a donut. I'm going to colour the outer circumference red and the inner circumference blue. Which one's longer? So clearly the outer one, but you notice how they are in contact the whole time. So it's possible to have two objects of different sizes always touching if the long one goes on the outside. Okay, so back to the heat detector. As the bimetallic strip gets hot, it bends to the right. If it bends enough, because it reached a certain temperature, it will complete the circuit and the bell rings. Ding. Alright, next one. Have you ever wondered why trains go da-dum, 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 da-dum? Okay, your smooth car ride disturbed by comb-like structures in the floor. Well, that picture top right is not some crazy slalom for trains. The tracks are laid down in long lengths, 500 meters of continuous metal maybe. Now this would not be a problem if they always stayed the same temperature. However, as they heat and cool in day and night, they change length. Now if you've got a piece of spaghetti uncooked and you squash the ends in, what's going to happen? It's going to buckle. If you keep pushing, it's going to break. And this is what the tracks can do if the engineers get their maths wrong. So what they do now is they put gaps in the track, or the road in this case. And what that means is that as the track expands, it doesn't hit the next piece and cause a build-up of stress. Alright, and okay, who doesn't want to fly away in a hot air balloon? Carefree. Well, if they weren't so expensive. This is a relatively example. This is a relatively simple one. We have a heater that heats air. As the air temperature goes up, the particles gain kinetic energy and move around more, taking up more space. The particles spread out. And so the gas has expanded. It has become less dense. Less dense gases rise above more dense gases, so the hot air balloon goes up. And if you want to take this up a level or two, try to think of a way to steer one of these things. Now with this last example, we're looping round to where we started. This time though, we're going to expand a liquid instead of a solid. What difference will that make? So how will that small change affect the behaviour of this being a liquid. Well, hopefully you thought about the particles. In a solid, the particles are close together and vibrating. Supplying energy makes them vibrate faster and take up more space, but not a lot of change really. The expansion is quite small. In a liquid, the particles are moving and they move faster with heat, so that's quite a bit more expansion. In gases, well, that's a very big expansion really. So in this one here, we're going to get more movement here, which is a good thing. If the water coming in is hot, the metal tube conducts heat up to the oil. The oil will expand and it will push the metal rod down, which opens the valve, letting more water through. Okay, and that will release the hot water. Once it's cool, the spring pushes the valve shut again. So there's 5 examples of how we can use thermal expansion, and we haven't even got onto thermometers yet. There's quite a lot in that though, so I'll save thermometers for another time, and what you should focus on at the moment is making sure you really understand these examples and that you can explain them clearly. If you understand something properly, then you should be able to explain it fully and clearly. So give that a go. Try speaking it out. Explain thermal physics, thermal expansion to your dog or your cat. Don't worry about your fish though, because fish have got terrible retention.